Climate models are mathematical representations of the world we live in, and creating them is all about the laws of nature. Understanding those laws and how they have influenced the Earth's past is the key to creating climate models that can accurately predict the future of our planet. Some climate modeling begins with an adventure to WAIS Divide, a research station on the West Antarctic ice sheet, where for 3 months every year, scientists drill into an enormous glacier, collecting samples of buried ice that date back tens of thousands of years. Shipped across the world to the National Ice Core Laboratory in Denver, Colorado, ice cores from WAIS Divide become part of a giant library. Each one like an ancient manuscript waiting to be interpreted. The cores contain information that holds the key to successful climate modeling. They tell us how changes in atmospheric greenhouse gas have influenced our climate throughout its history. They tell us how climate has changed naturally before human activity played its role. But extracting that information takes a team of scientists. Ed Brooke, a researcher at Oregon State University, measures CO2 concentration by analyzing samples of ancient air. That air was trapped in tiny bubbles when the ice formed from compressed snow in the distant past.
This is the system that we use for measuring carbon dioxide in ice. We take a small piece of ice out of our freezer and we put it in this crushing chamber.
Before crushing the ice, the chamber is tightly sealed and ambient air is pumped out. This isolates the sample of ancient air released.
What happens then is that air is transported into a gas chromatograph which measures carbon dioxide concentrations.
Scientists track the age of a core by counting its annual layers, which are measured very precisely by changes in electrical conductivity of the ice across summers and winters. The final piece of the puzzle is change in temperature, which can be determined by 3 different methods.
Maybe the easiest one to understand is if you have a frozen turkey and you put it in the oven and you heat it for an hour, it's still cold in the middle. And if you were to drill a hole in your turkey and put a thermometer in, you'd say, wow, it's cold in the middle. This turkey has not been in the oven forever. At one point, it must have been in a colder place. If you drill a hole in Greenland or in Antarctica, and you go down a mile or so, the ice is a little bit colder than it should be. And it's colder than it should be because it hasn't warmed up from the ice age yet. And in the same way that the turkey was in the freezer, the ice sheet was in the freezer of the ice age. And you can learn how cold the ice age was from how cold the ice is in the ice sheet now. That's one. There's a couple more as well. And so we start putting together all these different thermometers that you can use. And what we found so far is they agree with each other.
By studying how temperature and CO2 concentration have changed over time, scientists can determine how they are related. Findings show as CO2 levels increased, so did temperature. And when CO2 decreased, temperatures decreased as well. That information is very useful to climate modelers. Just as climate models can be used to predict the future, they can also simulate the past. By comparing the actual data collected from the ice core record to the numbers calculated by computer models, researchers have shown these models to be highly accurate. This gives scientists the confidence to employ those same models for the prediction of future conditions. But why does our climate change? What are the factors that influence its variability?
The amount of energy we get from the sun changes. I think we can understand that very simply when we look at summers and winters. When we're in a summer, we're tilted towards the sun and we get more sun's energy in the northern hemisphere. In the southern hemisphere, it's winter because they're tilted away from the sun. We get the same kind of thing happening over thousands of years as the Earth's orbit changes. So imagine at a time we are farther away from the sun, we get less solar energy. And there are times when we're closer to the sun, we get more solar energy. When we're closer to the sun, we have a warmer planet. When we're farther away from the sun, we have a colder planet. It turns out that when the Earth is warmer, when we're closer to the sun, we also have higher levels of CO2 in the atmosphere. Why is it? that when we have a warmer planet, we get more CO2 in the atmosphere.
One reason is that as the planet warms, the ocean's ability to absorb CO2 decreases. Imagine a recently opened can of soda. Over time, carbon dioxide moves from the soda water into the air, leaving the soda flat. This happens because there is a higher concentration of CO2 in the soda relative to the surrounding air. However, if there were a higher concentration of CO2 in the air, carbon dioxide would move in the opposite direction, into the soda. Apply that same principle to the ocean. Because there is more CO2 in the atmosphere than at the surface of the ocean, carbon dioxide mixes into the water. But as the planet warms, ocean currents change, altering the exchange of CO2 between the air and the water. Changes in the amount of sea ice and the biosphere also influence the amount of CO2 in the air. An increased concentration of carbon dioxide makes the planet even hotter, and that is due to the greenhouse effect.
In a greenhouse, we want to keep the air warmer than it is in the outside world. On our planet, when we add greenhouse gases, we get a warmer planet than we would without those greenhouse gases. Now, why is that? What's the simple physics behind that? All molecules have a characteristic frequency of vibration. They only absorb that energy that vibrates with the frequency that they like. So if you've got a molecule that doesn't care about the sun's visible light coming in, but does care about the Earth's outgoing infrared radiation, you've got a greenhouse gas. CO2 absorbs infrared radiation and is therefore a very powerful greenhouse gas.
More CO2 in the atmosphere traps more of the Earth's radiant energy, and that means higher temperatures. In the past, rising temperatures have been set in motion by changes in the Earth's orbit, and then amplified by the subsequent increase in CO2 released by the oceans. But since the Industrial Revolution, CO2 has been pumped into the atmosphere more rapidly than at any other point in the past 400,000 years. We have bypassed the Earth's natural cycles. Our environment is a system. One small change, like temperature, can lead to a chain reaction, having a big impact on rainfall and farming practices, or the polar ice caps and sea level. Studying climate change is about our place in that system. It's about understanding how nature impacts our lives and how we impact nature, so that we and all living things can continue to thrive on this planet we call home.